So hello everyone. So today we are going to start means we are going to continue the wave optics, right? So last class we have discussed wave optics up to the law of reflection and law of refraction, right? So today we will continue from the next. So next is we are going to see the superposition of waves. That means some concept of waves we will see which you have studied in grade 11. Okay, that means superposition of wave, condition for maxima, condition for minima, phase changes upon refraction and all that we will discuss. Okay, so let's discuss this superposition of waves. Suppose that this is a source of wave and this is another source of wave and this is a point P, and this distance wave is going to travel from here to here, and another wave is going to travel from here to here, right? So this path difference, first of all we should understand path difference. So what is path difference? Path difference, path difference. So path difference means S2 delta x means S2p minus S1p. Okay, path difference. Now S2p minus S1p part difference. This part difference is related with phase difference delta phi. Delta phi is k times of delta x. K is same as 2 pi by lambda. In the wave equation you have studied that, right? Phase difference. And these two waves can be represented as the first wave y1 and second wave y2. We can represent as a1 sine kx minus omega t plus phi 1, and second wave is a2 sine kx minus omega t plus phi 2. So phi 1, phi 2 are nothing but the initial phase, right? And kx minus omega t, this entire angle is known as phase. We have studied that in wave, right? So this difference of this angle, that is called phase difference, delta phi. So according to the equation, this delta phi is equal to phi 2 minus phi 1. That's the phase difference. Okay. Now let us understand, and you already know the concept of leading and lagging. Leading and lagging, you know, if this value is more, suppose this value is more values, right? So that will be leading. For example, suppose if I take time 0 and x is equal to 0 and I try to draw the phasor diagram of this. So this represents A1 amplitude of first wave, and this is the initial, right? Phi 1. Phi 1 is initial phase. For second one, it may represent A2 and this represent phi 2, right? So the phase difference delta phi is this only, right? Phi 2 minus phi 1. And in order to solve these two vectors, you know what you need to do? You need to do the resultant. So that's how you will calculate the resultant amplitude. Resultant amplitude is given as root under a1 square plus a2 square plus 2a1 a2 cos of delta phi. This is how we calculate the resultant amplitude vector sum, vector addition, right? Similarly, and we know that the intensity is proportional to amplitude square. This already we know. Intensity is proportional to amplitude square. So first intensity is proportional to first amplitude square. Second wave intensity is proportional to second amplitude square. So resultant intensity will be proportional to resultant amplitude square. So if you do that, in that way, we can calculate the resultant intensity as I1 plus I2 plus 2 root I1 I2 cos of delta phi. This is how you will calculate resultant intensity and resultant amplitude. And now comes the important thing about what is the resultant wave. So resultant wave, as you can see, we can represent the resultant wave by equation also, because in general the resultant wave is the sum of y1 plus y2. So when you add this vector sum, you can represent the amplitude of resultant and then everything will be same, sin kx minus omega t plus this angle can be written as alpha, right? And what is alpha? That alpha is nothing but the angle of this, which is alpha here. This can be calculated. Alpha definitely can be calculated from this diagram. How can you calculate? Because this angle between this angle between them is alpha minus what? Alpha minus what? Alpha minus phi 1. Alpha minus phi 1. And you know tan of this angle alpha minus phi 1, tan is equal to b sine theta. You remember b means here a2, b sine theta, theta means delta phi, b sine theta by a plus b cos delta phi. So from here we will be able to do the calculations of this, the calculation of this alpha can be calculated from. Right, but what are we interested in? We are interested in finding the maximum condition, maximum intensity. What is the condition for maximum intensity? Let us try to go into that. Maximum intensity condition. So, condition for maximum intensity. Condition for maximum intensity. So, what is the condition for maximum intensity? So, in this formula, this cos delta phi should become 1. That means the condition this delta phi should be 2 and pi. That's the important condition. And if you substitute phase difference is 2 pi by lambda into path difference condition, then from here 2 pi get cancelled. Path difference condition must be n times lambda. N times lambda. So, for these two waves to combine and produce a constructive interference means maximum intensity, this delta x path difference must be n times lambda, or the phase difference must be 2 and pi. N is an integer here and can be anything 0, 1, 2, 3, 4, minus 1, minus 2, minus 3. N can be integer here. Note that n is called integer. N is an integer here. That's all. Okay, so this is the condition, and now we can also try to calculate what is the maximum intensity. So this maximum intensity of the maximum resultant intensity will give root I1 plus root I2 whole square. Okay, and maximum amplitude, resultant amplitude maximum will be A1 plus A2, just sum of the amplitude. Okay, similarly, what is the condition for minima also we'll try to calculate, we'll do that. Okay, so this is the maxima condition. Maxima condition means phase difference to and pi, path difference and time lambda, intensity maximum root I1 plus root I2 whole square, resultant maximum, right? Also note that if these intensities of the sources are equal, let us say I1, I2 are equal, then the resultant intensity can also be written as 4I1 or 4I2 cos square delta phi by q. This we need to know. After you simplify, this can be written like that. So if the individual sources have intensity, so in that case, what is the maximum? So maximum value already I told, cos square maximum 1, so 4I1 will come. 4I1 or 2. Here also you can substitute. So if I1, I2 are equal, so root I1 plus root I1 will become 2 root I1. 2 root I1 whole square, 2 square means 4, 4I1 will come. Okay, but that's a general formula. If the intensities are equal, we can use that. Right. Yes. Are you getting this? Yes. Although I am going a little bit fast, but this is a topic which you have already covered in grade 11. That's why we can definitely go fast. Let us move next. Condition for minimum intensity. Condition for minimum intensity. Condition for minimum intensity. Minimum intensity condition means this cos of delta phi, this becomes minus 1. That happens when 2n minus 1 pi happens For that, phase difference is 2 pi by lambda into path difference. So 2n minus 1 times pi. So this condition, phase difference, and from here 2 pi cancels. So delta x becomes n minus half times lambda. That's the condition of path difference. So path difference condition can be calculated like this path difference condition. Okay. So path difference condition we can calculate like this n minus half lambda, and phase difference condition already I told it is 2n minus 1 times pi, right? That's how you can do that. Path difference, phase difference. And what is the intensity values also let us calculate. Minimum intensity. Minimum intensity. So minimum intensity become root I1 minus root I2 whole square, and minimum amplitude of the resultant minimum amplitude is A1 minus A2, or you can write A2 minus A1, whichever is bigger. That's why we can simply write this as magnitude. Okay, minimum intensity means amplitude is mod of A1 minus A2, right? Because mod when you take it means both A1 minus A2 or A2 minus A1. Clear? Yes. Anybody else joining? I will allow anybody in between, but we will continue. Okay, done. So condition for minimum intensity is done, right? Condition for maximum intensity is done, right? So let us go next. Let us move next. Now, very important thing here is phase. Phase concept is very important, which you should know. Concept of leading in phase and lagging in phase. Lagging in phase. Concept of leading and concept of lagging. Very important concept. Very important concept. So here note that suppose two sources are there, S1 and S2, and we are taking a point P. So this distance from here S1P and this distance from here S2P. Okay. So whichever distance is larger, that will have larger phase, and whichever has larger phase angle, that will be leading. That is important to note that. Okay. So whichever has more path length, more the path length, more the path length, more the path length, more the phase angle, more the phase angle, and it will be leading. It will be leading in phase. Leading in phase. For example, try to understand this concept. Suppose this S2P I am taking and S1P I am taking. S2P distance is larger. Let us say from your diagram also you can see S2P distance is definitely larger than S1P. So when you calculate path difference, you will take path difference is always bigger minus smaller. So S2P is larger, right? S2P is larger. So that means this wave will be reaching here. Wave will be reaching from this source to point P, and wave also is reaching from this first source to the point P. So both the sources are emitting the waves, and waves are reaching at this point P from both the sources, right? Now, the waves which is having more traveling more path, that will be leading. That will be leading. Okay. So that's the important thing. More the path length. Suppose S2 path is more. So that means this wave coming from S2 will be leading. That wave will be leading. Okay. That's what it's here. But this yes, Sam, no doubt. 11th is also there. I have mentioned the time, na, Gitu. Right. After this session, we will have. Right. So this is the path length. So now I told you, let us say that this wave coming from here is y2, and this wave coming here is y1. So if this distance is larger, so y2 is leading, y2 is leading, and y1 is lagging. That is the meaning of leading and lagging when we talk about the path. So if paths are given, we will be able to figure out which is leading, which is lagging. Okay, that's the important thing. Okay, done. Then let us go to the next. Let us go to the next. Now, what about in case of reflection and refraction? We need to understand this is important concept. How the phase changes, how the phase changes in reflection and refraction. So, suppose if there is a wave going and it is going to reflect. So, suppose it is a denser medium. Note that it is a denser medium and this is a rarer medium, rarer, and this is the boundary. Suppose a wave is going from denser medium and it is hitting and it is reflecting. Okay, note that this we are talking of reflected wave. So this is the reflected wave and this is the incident wave. This one is incident, right? Incident. So the wave is going from denser medium to rarer medium. Okay, so this is a denser medium and this is a rarer medium, and this is the boundary. This is the boundary. So it is true also for sound as well as light. So if wave is going from this medium to that medium, that means from denser medium to rarer medium, so reflection happens here. So if you see reflected wave, uh, so reflection is happening at the rarer medium. Try to understand reflection is happening at the, because it is going in denser medium and it is hitting the rarer medium. So reflection is happening at the rarer medium. So this reflected wave will it have any phase change or not? That is what we need to understand. This reflected wave has no phase change, no phase change. Okay, as compared to the incident wave. So incident wave and reflected wave, there will be no phase change. That's important thing to note. Okay, but if the reverse happen, then there will be phase change, that we need to note. Suppose for example, if we have this as the boundary, and let us consider that this is, let us say that this is rarer and this side is denser. So that means wave is going from rarer to denser. Okay, rarer to denser. Suppose this is the incident wave, and this is the reflected wave. This is the reflected wave. So if reflection is happening at the denser medium, wave is traveling already in the rarer medium, then it is hitting denser medium and reflecting. This reflected wave has phase change, has phase change of pi, or change path change of lambda by 2, because a phase difference of pi corresponds to a path difference of lambda by 2. Okay, that's what. Phase change means we have studied in sound wave. Now waves are traveling from one string to another string, denser to rarer, rarer to denser. So at the boundary reflection happens. So at the boundary the wave get inverted. If the wave get inverted, then there is a phase change. If the wave does not get inverted, then there is no phase change. So because when denser wave traveling from denser to rarer, there is no inversion happening, so no phase change. But when wave travel from rarer to denser, there is an inversion happening, so there is a phase change. Okay, so this rule we need to remember. It's important. Okay, done. Then yeah, so we will see its application. Of course, for NEET, that for NEET, they don't have thin film interference, but sometimes it may ask. We don't know. The thin film interference is an application of superposition. Okay, but for J main as well as for J advanced, that is there. The topic we will be covering that. Okay. So right now we discussed some important concept. Now we are going to move into what? We're going to move into YDSC, which is the main topic of this chapter, Young's double slit experiment. Okay, YDSC, and I will also be writing again some important points from notes because I don't remember everything. Young's double slit experiment. Let us start YDSC. Young's double slit experiment. YDSP. Young's double slit experiment. YDSP. Okay. Right. So, what are the assumptions here? That first of all, note the assumptions. Assumptions. First assumption is that coherent sources are there. Coherent sources. Coherent sources. So what happens? The setup is like this. There are two slits, very small width, and the distance between the slits is, let us say, d, right? And there is a screen here. This is a screen, and from here, there are rays coming. Light rays are coming and hitting everywhere. It is coming, but from this small opening or the slit, light will be passing. So from here the waves are created, and these waves go here, and similarly waves from here also goes in all possible direction, not only here but everywhere. First I am showing just only one particular point. So any point on the screen, if you take, it is illuminated. It is illuminated from both the slits. So waves coming from this slit and this slit, let us call this as slit 1 and this is slit 2. So waves coming from both these slits illuminate the screen, and any point on the screen is, you know, it is it is shining or it is dark or it is bright. It is because of the waves coming from both. So both the waves coming from these two slits are combining at that point, and interference or superposition is happening. Right, so that's the main thing. We'll go more in detail about that. Okay, and the distance between this screen and the slits, that is capital D. Okay, capital D, and this is like the axis of this experimental setup. This is the axis. This point you can consider as O. This can be taken as x-axis. This can be taken as y-axis, like this. Okay, will be coming into more detail. So first assumption is the coherent sources. These two slits are acting coherent sources. What is meant by coherent sources? Coherent sources means, suppose this is the first source and this is the second source, right? Second source. So the phase difference delta phi, phase difference is going to be constant. Phase difference does not depend on time. Delta phi does not change with time. Change with time. That is what it is. Okay. Then what is the next assumption in this YTSC? Second point assumption is monochromatic. Monochromatic. Monochromatic sources. Monochromatic sources means the same light. Same light means you cannot use white light. White light is a mixture of all the 7 colors. But we need to use only one single color or single wavelength. If you are using red color, so both this slit red color only must go. It's not that here blue will go, here red will go. No. Monochromatic means single wavelength. So it should have single wavelength. Single wavelength. Okay. That's important idea. Then what about that? Next. Yeah, these are the important things. Okay. Then write the condition for observing interferences. Condition for observing interferences in YDSC. Condition for observing interferences in YDSE. What are the conditions for observing interference? Initial phase difference between the interference must remain constant. Already I told that delta phi must be constant. Again I am repeating. That means coherent sources. Coherent sources. That's the first condition. Second, otherwise, suppose if the delta phi is not constant, then what will happen? If delta phi is not constant, then interference inter interference is not sustained. That means we will not be able to observe maxima minima. A kind of pattern is forming on the screen. That pattern we will not be able to observe it because that pattern itself will be changing with time. So if the phase difference is constant between the two sources or they are coherent sources, there will be a definite kind of pattern will be observed on the screen, right? That's what it is. Then frequency and wavelength two sources must be equal. That's what it is. Okay. Monochromatic condition. So frequency and wavelength of the two sources two sources must be equal. They must have same frequency and they must have same wavelength. Okay. If not, the phase difference will remain constant and so the interference. Again, the same idea. This is not happen, so there won't be any phase sustained interference will not be there. Okay. Then monochromatic condition already I told monochromatic. Okay. This eliminates the overlapping pattern as each corresponds to one negative pattern. What happens if the wave is not monochromatic? Suppose, for example, we are using white light. White light interference is a very important topic for NEET as well as JEE. Although in NCERT they have mentioned very briefly in one solved question. In one solved question they have mentioned very briefly, but question have come both in JEE main advanced as well as NEET. Okay, we will discuss that. So, what is the idea of the light is not a monochromatic light. So, if light is a mixture of two different colors or more than two different colors, then each color will produce its pattern, and the pattern of one color will overlap the pattern of other colors. Okay, so there is overlapping if monochromatic sources are not used. So, if monochromatic sources are not used, then there will be overlapping lapping of overlapping of fringes means patterns formed due to interference of each color or each wavelength. Okay, so that will be overlapping will happen and clear pattern will not be visible. Okay. Next, condition 4. The amplitudes of the wave must be equal. This improve the contrast. Okay, so the amplitudes of the waves must be equal in order to improve the contrast. Now you will say why it is necessary. It is not necessary, but contrast will be there. You need to understand that. Suppose if I use two sources of same intensity, then what is the maximum intensity formula? If you remember, you get what? Root I1 plus root I2 whole square, right? So now you apply this, so it will become 4I1, right? Maximum. But what about minimum? Minimum intensity of this if I use, so root I1 minus root I2 the whole square. So that will be 0 because both the intensities are same. So in maximum case, it is going to produce 4 times of individual, and minimum it will produce 0. So because on this, suppose for example, now I will tell this, you can see this black screen, right? On this black, if I write with white, there is a best contrast. But if I write with other color, like suppose I write on this black screen with black color, nothing will be visible, right? Nothing will be visible. So best is to write white color. So there is a contrast, right? Contrast. So bright means it's a maximum intensity, black means minimum intensity 0. Minimum is 0. So black, completely black means minimum. So that's what minimum intensity becomes 0 and maximum become 4 times of individual. So there is a big contrast is there. So on the screen you will be able to see bright fringes like white and dark fringes like black, right? And somewhere more bright will be there, somewhere less bright will be there, but maxima will be there as completely white, minima will be completely 0. Other colors, not color, other intensity will be in between that, in between completely bright and completely dark. So there is a contrast will be there. Okay. But suppose, for example, they don't cancel here. Suppose they are not equal, then they will not cancel. Not cancel means even the minima will have some intensity, and minima will also have little bit brightness. Then contrast will not be there. That is the idea. Okay. So for contrast, we should use that. Next important point, point number 5. Sources must be very close to each other. Must be sources must be very close to each other. Sources must be very close to each other. Otherwise, otherwise, due to small fringe width, small fringe width, the eye cannot, the eye cannot, cannot resolve the fringes, resulting in, resulting in uniform illumination. Okay? Uniform illumination. Sources must be close to each other. If the sources are not close to each other, they are very, very far away, then uniform illumination will appear to us, although patterns are formed, but we will not be able to distinguish the pattern form on this screen, right? It will look like uniform. Why? Because our eye will not be able to resolve. There is a concept of resolving power that we will see afterwards, but this important point that we have to remember. Okay. Then I think now we can go into this. Now we are going into more detail of this YDSC setup, and we want to find out maximum minimum conditions on the screen, right? So let us go into that. So there are two slits, basically two slits will be there, and this is the screen, this is the screen. This distance between screen and slit, capital D, right? And this is a source, this slit is a source S1, and this slit source S2. Okay. So generally what happens is that how do we produce this So we can keep some sources of light, or you can take plain light, means plain wavefront you can take. So the idea is that here rays are coming like this. This is going to behave like a source, and then now this is the central axis. This is central axis. So this point is O, right? This point is O. This point O is symmetrically located here. So distance between these two slits is D. Okay, and note that this capital D is very large here. Capital D is much larger than small d. So in NCRT, the proof is different, and the proof that we are going to do is going to be a shortcut approach, which will be applicable in most of the cases. Okay, so let us see that. So suppose I take any point here, and what is the goal of this analysis? Goal of this analysis is that this distance is y. I want to find at this distance y whether maxima is happening or minima is happening, and what is the condition for that maxima and minima that we want to find out. Okay. Okay. So let us take waves coming from here and here. Okay. So here we need to note one important thing is that these distances are very large. S1P, S2P are very large distances. Okay. So it's such a large distance that even this line or this line or this line, all these lines will be almost making the same angle theta with the horizontal. Very small angle it is. Okay, they are. This is a very far away distance. Don't think that these lines are um, converging. Actually, it's very far away. Means almost these lines are parallel lines. That's the approximation, and that approximation is going to do a very nice work. Okay, so we are going to consider that all these lines are parallel because these distances are very large, almost infinite. Okay, so now let us do the calculation. So what is the distance we want to calculate path difference? How to calculate path difference? Suppose if I consider this point P as the center and I try to draw a circular arc. Let me draw a circular arc like this. I will draw a circular arc like this. Okay. So note that this distance which I have calculated from here to here, this distance is how much? This distance is S1P. And from here to here also this distance is 1 feet. So this extra distance which we are getting, this extra distance is what is the path difference, this extra distance. Okay, now how do we calculate this extra distance? Because this is like a arc, means almost like a straight line it is. Try to understand this, because this arc is a very small, so this is almost like a straight line here. Okay, so when you plot a straight line, and here you need to note that this angle theta is angle between these two lines. So angle between horizontal is vertical, angle between this line, this is a perpendicular. So this angle is also going to be theta. That is what we need to note. That angle is also going to be theta, and this distance is d. This distance is how much? This distance is d, and this is going to be a right triangle. So this will be d cos theta, this distance will be d sin theta. That's what is the main thing we need to understand. This distance is d sin theta, and this is what is the path difference delta x. I hope you got this idea. This path difference, very important concept, path difference. So once you got this idea of path difference, d sin theta is equal to path difference. Now you can apply the condition for maxima. For maxima or for maximum intensity, for maximum intensity, for maximum path difference condition is n times lambda. So d sin theta must be n times lambda, and because the angle is very small, so we will write sin theta as theta, and theta is equal to y by d. Note that theta can also be written as y by d is equal to n lambda. So from here you will get y is equal to n times lambda d by d. Very important formula. y equal to n times lambda d by d, where n is the nth order maxima. Nth order maxima. This we need to remember. That means if I put n equal to 0, if I put n equal to 0, I will get y equal to 0. So this point y equal to 0, this point is called central bright fringe. This is called central bright fringe. Central bright fringe. Similarly, if I put n is equal to 1, so this distance I will get from here as lambda d by d. This is called first bright fringe. First bright fringe. Similarly, uh, first bright fringe. Bright fringe. Similarly, if I take next second bright fringe, so this distance will become equal to 2 lambda d by d. Okay, this I will be getting as 2 lambda d by d. This point I get first bright fringe, second bright fringe. This distance is lambda d by d. This distance is 2 lambda d by d. These are the coordinates I am writing. Okay. So in general, I have taken this distance as y. Note that this distance I have taken as y. So here anything can happen. Y can be first bright fringe, second bright fringe. So for bright fringe, we got this condition y is equal to n lambda d by d. N is 1 means first, n is 2 means second, n is 0 means central bright fringe, n is 0 means central bright fringe. Similarly, the same bright fringe will also exist here. Note that if you go below, n can be taken as minus 1 also. So this is also the first bright fringe, so do not get confused. This is first, this is second, this is second, first, all this like that. So similarly, pattern is existing above and below. So symmetricity is there. Same pattern of bright fringes above and same pattern of bright fringes below, right? That is what we have to understand. So bright fringe means what? Bright fringe means here maxima will happen, and what will be the condition of minima? Let us now also apply the condition of minima. For minimum intensity, let us apply. For minimum intensity, path difference condition is how much? N minus half lambda. Remember, n minus, so again d will be y by capital D is n minus half times lambda. So from here you will be getting this y is equal to n minus half lambda d by small. That's the condition of y. So here also y you can start putting 1 2 3 4, so you will be getting the minimas. You will be getting the minima. So suppose on this screen, and this is y equal to 0, which is central bright fringe. Central bright fringe. If I substitute n is equal to 1 here, that means it will become half. So this is the first minima, first dark fringe. First dark fringe. So first dark fringe distance will be half lambda d by d. Okay. Similarly, next will be 3 by 2 lambda d by d. This will be second dark fringe. Second dark fringe. Like that, it will keep on happening. Below also the same pattern will be there because symmetricity is there. So the below also first dark fringe. First dark fringe will happen at the same distance half lambda d by d. You may put minus because it is below y coordinate. Here also you can put minus, right? So minus 3 by 2 lambda d by d, second dark fringe. But remember, in between dark fringes we have bright fringes. Remember that. So here at this point lambda d by d, this distance is the first bright fringe. First bright fringe. And similarly next here second bright fringe. This is 2 lambda d by d, second bright fringe. Okay. So like that. Similarly below also here first bright fringe, here second bright fringe, like that. Okay. So central maxima is there, then first dark, then first bright, then second dark, then second bright, like that. Similarly above, similarly below, same kind of pattern will be formed. Clear? Yes. Oh, your camera, some issue is there? Okay. Laptop, huh? Might be some issue will be there. It's okay. Yes, some issue might be there. Okay, so don't worry about it. It's okay. If your camera is not working, that's not a problem, but you are able to see here everything, right? Okay, that's fine. So this is what about the YDSC setup. We have to remember this is formula for nth order minima. Nth order minima. Nth order minima and nth order maxima. We must remember this formula. Okay, now sometime question will come, how many maximas can happen and how many minimas can happen. Look at this formula d sin theta and lambda. Just look at this. They may ask you how many maximas will form. How many maximas form in YDS? How many maxima form in YDS? So if you see the part difference condition, d sin theta and lambda, this is the condition for maxima condition. Now I know sin theta is equal to n lambda by 2, right? I know because, and we know that sin theta will lie between -1 to +1, correct? Minus. So if I can substitute lambda d by d, if I substitute this condition, then the value of n will lie between minus d by lambda to plus d by lambda. Okay, value of n will lie between minus d by lambda to plus d. Of course, here note that one side is above, one side is below. That's why minus is coming for below, plus is coming for above, right? That we have to note. But suppose let's take one example. Suppose they give the distance between the slits. They give the distance between the slits as, let us say, 6 millimeters. This is the distance between slits, and the wavelength of light which is used, lambda, is, let us say, some nanometers. How many nanometers? Let us say 900 nanometers. Okay. And they will ask how many maxima comes. How many maxima? Total number of maximas they ask. Total number. So this is central bright fringe. Some maximas will be above, some maximum will be below. So we have to count the total number. So first let us calculate d by lambda here. So what is the factor d by lambda? D is 6 millimeter 10 to the power minus 3, and this is 900 nanometer means 10 to the power minus 9. So from here 3233 into 10 to the power minus 7 plus 7, 7 minus 3, 4. So it is almost how many? How much? 20 by 3, let us say, into 1000. 20 by 3 is how much nearly? It is 6.67, let us say, into 1000. So nearly 667 you can also take. So nearly 6, uh, 7 approximately it may come. Okay, 6,667. Correct. So if you consider this side, this side. So you need to make sure that this value of n should be less than that. Less than that means how? Of course, it can come in fraction, right? Because if you take 6.66667 something, it will come. Correct? How much actual value will come? Can you tell me? Let us say if I keep on dividing, so 6.666, right? Like 6, or let us round off the last 7. So into 1000. Then it will come 666.7, right? But we want value less than this, and integer we want. So if you count from 1 to that much, so 1 to that much will be 666 only. Integer we want, okay? And including 0, if you include 0 means you have to add extra 1. So 666 plus 1 means, if I want total number, note that total number means this side also is there. So I need to multiply 2 times of this. So total number of fringes I can calculate. This is total number of fringes. Total number of fringes. Total number of right fringes. So 6 into 12, 6 into 12, 113, 6 into 12, 113 plus 1. So the answer will be 1333. But if they ask only total number of bright fringes above central bright fringe, total number of bright fringes above central bright fringe, then we have already got 666, and I want 1 means this is including bright fringe, including central bright fringe, including central bright fringe. So if you include that, then it will be 666 in 7. Okay, that's how we have to do it. I just given some value to do some calculations. Okay, so like that we will be counting the number of fringes in the problem. Clear? Okay, then what else? Now, very important thing is that shifting of fringes. Shifting of fringes. Also, before that, we should know what is called fringe width. Before that, we should know fringe width, beta. Fringe width is the separation between consecutive right fringe or consecutive dark fringe. So separation between consecutive bright fringe and consecutive dark fringe, that is what it is. So if you see bright fringes on the screen, so bright fringes are forming as lambda d by d next to lambda d by d, like that. So distances between them is lambda d by d. This is what is called beta. Even for dark fringes also you can calculate. Dark fringes here is lambda d by 2d. This is 3 lambda d by 2d. Here also the distance between them is lambda d by d. That is what is beta. So distance between consecutive bright fringes or consecutive dark fringes, that is what is beta. So here we should note that beta, which is lambda d by d, this beta fringe width can shrink if lambda can change. So if you can do the experiment, Young's double slit experiment in water, if you do, or some denser medium if you do, lambda will decrease. Okay, so we note that fringe width, note fringe width, fringe width will shrink if YDSC is done in denser medium. In denser medium. So if you perform YDSC, Young's double slit experiment, in denser medium, then what will happen? You need to understand that fringe will shrink, right? That's what it is. Because lambda will change. So suppose lambda in a medium, you know that lambda in a medium is lambda in vacuum divided by refractive index. This you know. Just like speed changes, same way wavelength also changes by the same factor. That's what it is. Then shifting of the fringes. Then we are going into the topic of shifting of fringes. Shifting of fringes. Suppose this is YTSC setup. This is central bright fringe, central line. Now suppose if I put a slab here of thickness 2 and refractive index means, so what happens to this point P? Now this path, this is S1, this distance is S1 and this distance is S2. So now S1P will not be same as it was before putting this slab. Previously S1P was different and now S1P is different. So, but S2P is not going to change. S2P in vacuum is still same because we have not put any median before it, right? Okay, so that's what changes is going to happen. So S1P dash will become how much? First of all, find out distance in vacuum. So S1P minus T you have to do to remove this. Now this distance thickness you have to multiply, add extra factor mu2 which is called optical path. So you need to do this calculation. So this will come as S1P plus mu minus 1 into T. So this is what it is. S2 P dash remains same as S2P. Now let us calculate the path difference. So path difference now which we want to calculate is S2P dash minus S1P dash and S2P minus S1P minus mu minus 1 into T. And this S2P minus S1P, that distance is d sine theta which we have already calculated, right? So mu minus 1 into T. And now we will apply the condition sine theta is very small, so this is y by capital T minus mu minus 1 into T. And for maxima condition we will put this as n lambda. For maxima we will put it. So now if you simplify this, what result do you get? You get dy by capital T is n lambda plus mu minus 1 into T. Now if I multiply, calculate y, so n lambda d by small d plus mu minus 1 into T capital D by small d. So this formula tells us many story here. One of the main story here is that previously the value of maximum was n lambda d by d, but extra factor is getting added up. This extra factor is the shift here. So that's the formula for shift we have to know. Shift in fringes is given by this formula mu minus 1 T times capital D by small d. Okay, like this. Right. That's what we need to calculate. And suppose if they ask how many fringes shift, how many total fringes are shifting, so you can divide this shift divided by fringe width also you can do that. Okay. So within that, how much it can happen, we can do that. How many? But generally they will ask shift formula only, so we'll calculate this. Right. That's what it is. So most important thing is that if you are putting, for example, here try to note that suppose if we have two slits like this and this is vacuum, so let us say consider that this is maxima is happening here, central bright fringe, this is central bright fringe previously. Now suppose you put a slab here, now what happens is that this shift will happen in this direction. So central bright fringe will now come here, central bright fringe will now come here, and this is the shift that is happening, so not only central bright fringe, everything, all the maximas will shift, right? Previously suppose here first maximum was there, now first maximum will also go up, everything will go up because in that side you have put this slab. Clear? Are you clear about this? Yes. Right, so that's a very important result. So shift we have completed. YDSS setup is there. Now there is a question of missing frequencies. Let us take that missing frequency. Missing frequency in front of one of the slits. So suppose we have two slits S1 and S2, and this is central bright fringe. Central bright fringe. Now suppose in front, exactly in front of this, we are saying that some frequencies are missing. That means for those frequencies there is a minima is forming. So this distance y is equal to d by 2, because this distance is total distance is d. So this distance is d by 2 and this distance is d by 2. So y is equal to d by 2. Y is equal to d by 2 is a condition for minima here. Now try to apply minima condition. Minima condition y is n minus half into lambda. Lambda d by t, that's the condition. So if you apply here, so you will be able to calculate lambda. Lambda will come as t square by 2 capital D n minus half. Now try to put the values of small n here. Let us put 1. So lambda will be d square by 1, you put half minus half capital T. If you put n is equal to 2, so 2 4 minus 1 3. So d square by 3 capital D. D square by 5 capital T. Right? So you can see that odd numbers are coming in the denominator. So these are the frequencies which are missing at that point. Are you getting that? Why missing? Because minima is forming for all these, right? For all these minimas are forming. Done. What else? What else is remaining in this YTS setup? I think most of the topics we have covered in YTS. Yeah. Okay. So YTS is over. Then one important thing was missing. That's what I was thinking about. So the slit width. How does the slit width means? I'm talking about the slit width, slit used in there. Okay. The distance between the slit is d, of course, but suppose the width of the slit is b. Width of the slit is b. So here the intensity is proportional to area. That is what we need to note. Intensity is proportional to area of width. Area of slit or opening. Opening. Suppose if I consider this as a circular slit, I can take a square slit of rectangular slit, but if I take circular, this will become radius or diameter. So square it will be. So intensity will be proportional to square of this. Okay, like this it will become. That means if I reduce the width, if I reduce, I make it half, so it will become 1 by 4 times intensity. Okay. So, for example, suppose the type of question comes. Suppose if there is a equal width, let us say B and B. So that means let us say intensity is I1 and I1. Same intensities are there. So maxima forming at the central bright fringe, maxima happens, and central bright fringe intensity is maxima, resultant intensity is maxima, that is 4 times of I1. But now suppose I make this B half. Let us say I one of this slit I make as half. So now in this case I make half and this become B. This is B only, this become B by 2. So because I have made it width half, so its intensity become 1 by 4, and this intensity is I1. Now let us use the formula for central right fringe. Now central bright fringe, what happened? We have to use the formula for resultant maximum. Remember the formula for maximum was root I1 plus root I2 whole square. Remember that? Try this now. So root of I1 by 4 plus root of I1 whole square. Calculate this. How much it will come? So now it will come as half, it will come. So root I1 will come. This is half plus 1, 3 by 2, 9 by 4 it will come. Okay. This is how it will be coming, 9 by 4 of I1. So, So this is how it will change. So if you make this slit width half, previously the intensity was 4I1, now intensity will be 9 by 4I1, right? Are you understanding it? So this type of questions come in it. Right. So I think we have discussed anything. The YDSC is completely over now. YDSC is over. Now single slit diffraction pattern quickly we can do within 5 minutes. Okay, it will not, because I will not go into the proof of that. The proof of that is very lengthy. But also one more thing here in YDSC, which uh, in YDSC intensity distributions also I will show intensity distribution. Then we'll go to single slit. Intensity distribution. Intensity distribution on string. On string. So this is the screen here. This is the screen, and suppose, for example, this is the point central bright fringe. So you know the intensity distribution happens like this way. This is maximum. Okay, like this. Like this. So these points which you can see here, these are minima. These are minima. This is first dark fringe. This is also first dark fringe, but this is below. This is second dark fringe. This is also second dark fringe. But if they talk of maxima, so this is central bright fringe. Then this is the first bright fringe. This is the second bright fringe. Like that below also. This is the first bright fringe. Here for the second bright fringe, other things will happen. So symmetrically, you can see all the maximas have the maximum intensity or resultant maximum intensity 4 times of individual intensity. Where here we are taking that each of the slits S1 and S2 have same intensities I1, I1. I1, I1 we are taking because they have the same width system. Clear? So that's what it is. I think most of the things are here. Then what about this white light interference is also there? Let us cover that white light interference also. White light interference. White light interference. So in white light interference in YTSC, in white light interference, what is going to happen? So in white light interference, what will happen? In white light interference, okay, this is the central bright fringe, and now white light interference means you are sending white color light. So white color light is made up of all the different colors. So each color will make its own pattern, but the thing is that you may think which y will be. You may use here, this is the most misconception, y is equal to lambda and lambda d by d if you use for maxima. If you say that lambda is more, so y will be more, so red will be away. But no, this misconception is what we need to clear. Okay? So red fringes will observe here, central bright fringe will look completely white. Okay, near here you will find out reddish white, violet, indigo, blue, green, yellow, orange, red. Orange is white, orange is white, right? Then gradually all this color green, violet, indigo, blue, green, yellow, or yellow is white, yellow is white. Then violet, indigo, blue, greenish, violet, indigo, blue, green, yellow. Greenish, white, like that. And similarly, all that white will be coming. Then last here, bluish white. Bluish white. This is what a pattern you have to note that. So violet, indigo, blue, green, yellow, orange, red. You can count from here. Violet, indigo, blue, green, yellow, orange, red. Violet is white and all that. So the red color will be found closer to the central bright fringe. That is the key. That is what they will ask in say main or you need to just choose the correct option. This is what you need to remember here. Okay. So red color, all they are going to be white only. Don't think they are not white. They will be white only. But what will happen is that the reddish color will come closer to this central bright fringe, and bluish color or violetish color will go away from this central bright fringe. Okay, so that's what we will be. Yes. Okay, so done. So let us wind up. We are winding up this session now. So then we are going to start grade 11 topics. Okay, give me 5 minutes break. Okay, we'll start in few minutes. Okay, just give me 2 minutes break. I have to send this also.